Wolfgang, just building on what Jens said, we know that Lactobacillus reuteri is an important symbiont. What's the mechanism of action? I think you've done some work here on with DSM 17938. What can you tell us?
Yes, well, we used a sort of ex vivo preparation to try and examine whether or not DSM has an acute effect and whether it's a neural effect. And so basically we have a water bath and we put a piece of intestine in there, and we can introduce the DSM, L. reuteri, into the lumen and look in real time what it does to motility, and particularly neural reflex dependent motility, peristalsis, which depends on the enteric nervous system. We videotape it, and on the right-hand side you can see we can summarize contractions over an hour by these hills, color-coded hills and dips. And it's clear that when you add this bacterium, it increases peristalsis, propulsive peristalsis, within 15 minutes. So it's an acute effect on the nervous system, and it increases frequency and velocity. So it has an acute neural effect on peristalsis, and it can do that. We have a model of constipation using opioid receptor agonists, loperamide. This constipates the gut, it reduces motility by 15%, and again, within 15 minutes of introducing this bacterium, we can overcome, in the presence of this opioid receptor agonist, morphine-like agonist, which really stops peristalsis almost by more than 50%. This bacterium can overcome, via a neural reflex, this slowdown to a large extent. Now, we've increased these numbers since then, but particularly frequency and amplitude is reconstituted. So this shows a direct therapeutic neural effect by this particular bacterium.
Well, I guess, we've been talking about manipulation of the microbiome, but you said there's an effect in 15 minutes. Pretty hard to change the microbiome in 15 minutes, so there must be some other mechanism going on here.
Well, yes, and we looked for a likely receptor that this bacterium might act on, and it turns out that the best candidate was initially a TRPV1 receptor. It's a pressure-sensitive receptor, it's a heat-sensitive receptor, and it's a receptor for spicy hot peppers. You're probably familiar with that. And also acidity. It's well represented in pain neurons in the peripheral nervous system, and actually throughout the body and brain as well. It is important because it's involved in a lot of pathology, particularly sensitization of pain signals and pain hypersensitivity, so that a normal stimulus could be perceived as painful. So in that system, anything that acts on this receptor, potentially down-regulating its open probability, would be therapeutic. And when we directly tested the effect of L. reuteri on pain neurons, we isolated pain neurons, dorsal root ganglion neurons, and recorded their current with patch clamp. So that's a direct measure of the excitability of pain neurons. And we squirted chili pepper, we squirted chili pepper on these pain neurons, DRG neurons, and we got a big response, and then a second response, which is decreased a little bit, and that remains constant. So this is how these nociceptors, pain fibers, are activated by capsaicin, by hot chili pepper, and is a measure, if you like, of the painful signal that's fed into the spinal cord. What we then did, we repeated that experiment, but then added DSM, 10 to the 8 colony-forming units per milliliter, which is a normal dose. And as you can see in C and D, these two panels here, in the presence of DSM, the excitation of these nociceptive neurons, of these pain fibers, is largely reduced. So this is almost as effective, actually, as an opioid analgesic. And if you summarize that, you can see on the right-hand side for a whole series of experiments, the reduction of the pain signal acutely, again within about 15 minutes, is 50%. Now we did other experiments where instead of looking at the neurons and the electrophysiology, we looked at the pain response directly in vivo, and again DSM blocked the response to distension and reduced pain. And so it's clear that not only is it a neural mechanism, but it targets a pain receptor, a chemoreceptor in the intestine.
So there's a variety of different things that we're seeing here: effect on peristalsis, effect on pain. Any other? How would you summarize all the effects that's going on here?
Yes, well, it looks like L-reuteri DSM 17938 really has a multifaceted, a multi-pronged effect, therapeutic effect on the organism when it is ingested. And so it clearly decreases visceral pain. We can demonstrate this in vivo, ex vivo, mechanistically by recording ion channel currents from neurons. And it also improves gut motility, potentially via the same receptor or maybe some others as well. It clearly also acts on the immune system by decreasing inflammation. So the therapeutic effect is a multi-pronged one, if you like, targeting the host after ingestion through a variety of systems, possibly first on the nervous system, then that's reflected by alterations in the immune system, and it also by competition and various other products it'll release, and it can alter the local composition of bacterial ecology in the intestine as well. So you can see it has acute, short-term, almost therapeutic drug-like effects, and all the way down to longer-term effects where it changes the ecology.
Great, thanks for that great summary. I'm sure there's a lot of clinical implications for this.